Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 2. In geometry, we are going to have to define our terms. We have to use the same words when we're talking about geometry. So we're going to need to do a lot of definitions. Our first one is a point. A point is the most basic building block of geometry. It has no size, it's just a location. We represent this point with a dot, and we name it with a capital letter. Here's an example of a point. This is point H. I can make another point and name it point L. A line is a straight, continuous arrangement of infinitely many points. It goes on forever, and we represent that with these arrows at the ends, that it goes on forever. The artist Paul Klee said, "A line is a dot that went for a walk." So we can think about that also in geometry. If a dot or a point keeps going and going in both directions, then it turns it into a line. We name a line using any 2 points on the line. So if this line has a point D and E, we can name it line DE. We generally write the line symbol above the line. And the line symbol does contain those arrows to let us know that it is a line. It goes on in both directions. We could similarly name this one as ED. There's really no reason why you'd have to go in one order or the other. So DE or ED for this line. Next, we have a plane. Not that kind of plane. One that looks like this, a geometric plane. It has a length and a width, kind of like a piece of paper, but it keeps going in all directions. It's a flat surface with a negligible thickness. It extends in both its length and its width. So a piece of paper that never ends, that would just cover the whole earth, that we can't even measure the thickness, that would be a plane. We usually name planes with this script letter. So this is like a fancy P. And again, we're going to have a lot of definitions. We usually try to define everything else in geometry from those 3 basics of a point, a line, and a plane. It's impossible to completely define those points and lines and planes, but we've tried and we've given some pictures. So now we have some more definitions. Collinear. Well, co usually means with or together, and linear sounds like line. So collinear means something on the same line. If I have a line right here, and I put a lot of points on it, and then I put a point up here and a point down here, and I name them points A, B, C, D, and E, which points are collinear? So the points here that are collinear would be point A, point B, and point C, but not point D or point E. At least they're not collinear with A, B, and C. D and E could be collinear if we make a new line. So if we made a new line here, now D and E are collinear. What about coplanar? I bet you've already guessed this one. It means on the same plane. So we draw our geometric plane. Just kind of looks like a square, and it's going off in both directions or all directions. And I have point A on the plane and point B on the plane. These are both coplanar. If they're collinear, they will always be coplanar because that line could be on the same plane. It's hard to draw 3D, but if I come off of this flat paper and like up here in the air, and I have point C up here, then that point C is not coplanar with A and B. What about a line segment? It sounds kind of like a line, and then segment would be like to take it apart or to have pieces of it. So a line segment is part of a line consisting of two endpoints and all the points that are in between or collinear. So if I take this line, maybe it's D, E, and F, so I could call it line DE, I could call it line EF, I could call it line FD. I can take any 2 points to name this line. If I just take part of it, I just want to segment this and just take part of it. I'm just going to take from here to here. I'm going to take this endpoint D and this endpoint F, and I'm going to have the line in between. Of course, it would still have E in it. So I'm just taking part of this line that goes on forever in both directions, and I'm just taking part of it. I'm taking a segment of it. So then DF would be a line segment, and I would name it just very similar. I would name it DF with a line segment symbol over it. Remember that this line would be DF with the line symbol over it, and this segment would just have the segment symbol. So endpoints are just points on the end of a segment. If we want to write the length of a line segment, we can write it in two ways. We can say that line segment DF is equal to, we'll call it 2 inches, or we could use this M in front of it and say the measure of DF is equal to 2 inches. So sometimes we use that little M in front to denote that we are measuring that line segment. We will also use it in angles as we continue on. If there are no units given, we can just understand that units are not really important in that exact problem. We could even maybe think of just if it's on a grid, that one grid segment is 1 unit. So you can put a unit in there. If it's not listed at all, you could just say units, or you can leave it with no units. You could just say that DF is equal to 2 if that's how the problem is given to you. What about congruent segments? Congruent segments are congruent if and only if they have the same length. So congruent segments have the same measure or length. The symbol for congruent is like this. So I could say that DF is congruent to segment NM. I could also name it MN, but I chose to go backwards and name it NM. But they're congruent. You can see that they have the same length because the measure of NM is equal to 2 inches. When their measures are equal, when they have the same length, then we can say that those line segments are congruent. We also spend a lot of time drawing pictures. So if this triangle is congruent to this triangle, then this side is congruent to this side. And this side over here is congruent to this side. Maybe it's an isosceles triangle, and these two sides are congruent to each other. We often make these markings on our drawings to denote congruence. So if it's the same number of marks, we can see that this line right here has 1 mark, and this line has 1 mark, and this one has just 1 mark, and this one has just 1 mark. Then all 4 of those segments are congruent. This line over here has 2 marks on it, and so that means that it's congruent to this other line segment that has 2 marks on it. Within the same problem, we can make these notations about how the line segments are congruent. If I had a rectangle, then I would say that this segment is congruent to this one, And this one over here is congruent to this one. Our drawings may not always be exactly accurate, but when we mark them with these congruent symbols, then we are showing that that's what we mean. A lot of times we'll see in our drawings that the problem will even say not drawn to scale. So while two things might look congruent, like these lines over here, maybe this looks like an equilateral triangle, but this one is marked differently, meaning we can't assume that it's an equilateral triangle just because it looks that way. We have to follow the markings or the identifications on that problem. The midpoint of a segment, let's draw a segment right here, and let's see if we can figure out what a definition for the midpoint would be. I'm drawing the midpoint right here. Where does it look like it is? It looks like it's right in the middle. The midpoint of a segment is the point on the segment that's the same distance from both ends. I could even mark that this side is congruent to this side because M is exactly in the middle. The midpoint divides or bisects this segment into two congruent segments. I've marked DM as congruent to ME. This segment is congruent to this one, so M must be exactly in the middle. The midpoint M bisects the segment DE. It divides it. Our last definition for today is a ray. A ray is part of a line that has one end point. So if I have a line, and I might have A, B, and C on it, I could have a ray AC. I would write it as this way. It means that the ray AC is actually only a part of this. It's from here going to the right forever. So it has an endpoint A, and then it goes on forever in the direction of C. So the ray AC is not equal to the ray CA. Get a different color and draw the ray. So CA, I'll draw in purple, would be from this point and continuing this direction. I didn't draw it quite on top. It would be on top of that line. But to show you that AC is the blue one that goes to the right, and ray CA would be this purple one that goes and continues to the left. I like to think of a ray as a combination of a line and a line segment. It has an endpoint on one side, but it keeps going on the other side. The last thing to think about today is the midpoint. The midpoint is halfway. We talked about being halfway on the segment. It's going to be the average of the 2 points. So if we have them on a coordinate grid, we could actually average the 2 points. If we want to find the midpoint between x1, y1, and x2, y2, we would use this formula right here. So let's find the midpoint of -1, 2, and 5, -4. First, I'm going to draw it and show you on our grid. So -1, 2 is right here, and 5, -4 is all the way down here. If I connect these with a very straight line, then I can estimate, what is about half? It looks like it'd be about here. So let's see what that is going to be. So the first point is my x1 and my y1. So I take the average of the x's. So I take x1 and x2. So I take this point, this number, and this number, and I average them together. -1 plus 5 divided by 2. That's my average. So a 5 minus 1 is a 4. 4 over 2 is 2. That's my answer for the x. That's this part right here. And my answer for my y is going to be the average of my y's, my y1 plus y2, y1 plus y2, or this one plus this one. So 2 plus a negative 4. And then I want to take half of it. I want to average between them. So 2 minus 4 is negative 2 over 2 is negative 1. That's the answer for my y. So if my line had been really straight, this would have been my midpoint. It's 2, negative 1. My midpoint is 2, negative 1. I averaged my x's and I averaged my y's to find out what I would have in between. That's it for today.